Let's think about a cycle A0, A1 up to AM-1, so an M cycle. And you'll remember from our last lecture what this cycle does. It's the permutation which sends A0 to A1, A1 to A2, A2 to A3, and so on until you get to AM-1, which gets sent back to A0. So what would the inverse of this cycle do? Well, the cycle sends A0 to A1, so its inverse should send A1 to A0. And the cycle sends A1 to A2, so its inverse should send A2 to A1. And so on until you get to the fact that the cycle sends AM-1 to A0, so its inverse should send A0 to AM-1. So in other words, we get the inverse just by reversing all the arrows in our picture, which means that the inverse of the cycle A0 up to AM-1 ought to be just the same cycle, only written in the opposite order. So that's what this theorem, which we're going to prove now, says. It says that if you take an M cycle, which you write as A0, A1 up to AM-1, then the inverse of that cycle is equal to another M cycle whose entries are just the A's written in the opposite order. So let's try and do a proof of this. And in order to do that, we'll fix some notation. So we'll call the original cycle we're thinking about C. There it is. And we'll let D be the cycle written in the opposite order. And then what the theorem is claiming is that C and D are inverses to one another. Now you will remember that what the definition of an inverse function is. The definition of C being inverse to D is that C composed with D and D composed with C are equal to the identity function. So that's what we have to prove if we're going to prove this theorem, that C composed with D and D composed with C are both the identity function. Now the thing about writing proofs is often it's not really that the idea is very hard. What's difficult is writing that idea down in a clear way in which other people can understand. And often coming up with a way to do that is harder than actually understanding the idea behind the proof. And this is one of those examples where coming up with a clear piece of notation actually helps us to write the proof more simply. So here is my notation. What I'm going to do is I'm going to extend the definition of these numbers AI. At the moment, so when we're defining C and D, only the numbers A0, A1 up to AM-1 mean something, and those are some distinct integers. But what I'm going to do to help me write my proof down is I'm going to define AM to be A0, and AM plus 1 to be A1, and AM plus 2 to be A2, and so on. So in other words, we let these numbers AI just repeat themselves after M steps. And similarly, going in the other direction, I'm going to let A minus 1 be AM minus 1, and A minus 2 be AM minus 2. So before we made these definitions, AM and AM plus 1 and A minus 1 and A minus 2 didn't mean anything, and I'm using this definition to give those things some meaning. And the reason that this is a helpful thing to do is because then, for any I, we have C of AI is AI plus 1, and D of AI is AI minus 1. Right, that wasn't true until we made these definitions, because if you apply C to AM minus 1, well, you get A0. So you don't get AM unless I've made this definition saying what AM is. And before we made this definition, AM didn't mean anything at all. So the point of making this definition is that these two things hold for any I, not just all the i's which are less than M minus 1, or all the i's which are bigger than 0. Okay. Now we've made our notation, we're ready to go in our proof. We're supposed to show that C composed with D and D composed with C are the identity. I'm just going to do one of those things and I'll leave you to do the other. So we claim that C composed with D is the identity function. Okay, and the proof of that claim is just to look at what happens. Well, first of all, let's look what C composed with D does to one of the numbers AI. So any I at all, what happens? C of D of AI is equal to, well, because I made this clever choice of notation, this is just C of AI minus 1. And I don't have to think about a bunch of special cases where what might happen if I was m minus 1, or what might happen if I was 0. I can just say that no matter what I is, D of AI is AI minus 1, and C of AI minus 1, looking at what I did just here, C of AI minus 1 is AI again. So C composed with D applied to AI is just AI again. And if you've got a number which is not any of the AIs, if J is not any AI, then from the definition of cycle, C of J is J again. And D of J is J again, because J does not appear amongst any of the things in my two cycles C and D. So again, in this case, C of D of J is equal to C of J is equal to J. Right, we've shown that for any number, whether it is an AI or whether it is not an AI, C applied to D applied to that number is just that number again. So C composed with D is the identity function. It doesn't change anything. If you do the exact same argument with C and D swapped, you'll find that D composed with C is the identity. So we've finished our proof because we've shown that both compositions, C composed with D and D composed with C, are equal to the identity function. So this is useful. It gives us an easy way to find inverses of functions which are given to us in cycle form. Moving on, we have an unfortunate fact, which is that not every permutation is a cycle. So let's look, for example, at this permutation here, S. This is a permutation in S4, and I claim that this is not a cycle. So to see that, let's draw our usual kind of diagram telling us what S does. Well, S sends 1 to 2, and S sends 2 back to 1 again. And S sends 3 to 4, and then it sends 4 back to 3 again. So you can see here that S itself is not a cycle. But what you can also see from this is S is the composition of two cycles. It's equal to the composition of the 2 cycle 1, 2 and the 2 cycle 3, 4. So we can say that S is, however, a composition of two disjoint cycles. And in fact, what we're going to show in the next couple of videos is that every permutation can be written as a composition of two disjoint cycles.